So starting off with math for tensors is that we can actually combine these parts and actually do things with them. That's the whole point of us learning linear algebra aspects. Good for granddad. Okay, cool. So we can actually combine them. So one thing to note, I kind of put a little note right here, is that NumPy is actually really good at combining tensors that kind of seem obvious to us, and it's something called broadcasting. So when we broadcast, it basically means it's like, well, technically, you need to make these matrices a certain shape to add them together, but NumPy is like, I think I know what you're trying to do, so it's going to go with it, which can be super helpful because then you don't have to like make, like, for example, if you want to add 1 to each matrix, you technically would either need to create a matrix with basically a bunch of 1s in it, or a tensor, or you have to define a whole new matrix or iterate through it. But what happens is that, well, NumPy says, well, you're adding 1. You technically can't do that. But I think what you're trying to do is basically add 1 to each element. So we'll see a little bit of that. There's a lot of subtlety to this too. And sometimes it can give you answers that you wouldn't expect. And sometimes it does things that you thought would work well, but that doesn't work well. So I'd strongly suggest going through the documentation to make sure you know how it works. Okay, especially if you come across when you're like, wait, something's not adding up right. It's probably because of broadcasting. It could be other things, but that's the main stuff. So, okay, I just made these couple matrices right here. So you can see that I have this matrix. I just multiply it by 10. So that way I just have different numbers. Okay, so we can start doing some math on it. The first thing, obviously, combining is addition. And when I say addition, that could also mean subtraction. Addition and subtraction are pretty much the same thing in this case for matrices because you can just multiply it by -1. So you like, oh, I guess I should mention that. We can multiply numbers onto this matrix, right? And if we multiply by 10, as you probably would expect, it just multiplies every element in here by 10. So you can see that's kind of how it worked. But now when we do addition here, I have our original matrix, the same matrix is defined up there. Is that right? Oh no, I'm sorry, it is a different, there are different matrices. So you can see I do have a 5 by 3. So they're slightly bigger matrices. So you can see, same idea. I can actually add them up with the same dimension. So you can see, well, you guys probably guess is that if I add these matrices together, or if you remember from school, this will add up element-wise since they're the same shape. You add 0 to 0, 1 to 10, 20 to 2, and so on, right? And you can see, if I add them up, you can see 0, 0, or 0, 11, 22, 33, and then goes on, basically just adding up this part, plus it's 10 times element. Pretty simple, I think, not too hard. This is the broadcasting I was talking about, a plus 100, you have a scalar, it'll do just add 100 to each element. So added 100 to 0, add 100 to 1, 100 to 2, all the way through to 14. Again, not too difficult, but it's useful in this case. Technically, you're supposed, like if you were to do like write this on like a mathematical paper, you would have to write a matrix full of 100s, which would be a pain if we had to do that every single time we had to program it. So that's why NumPy allows you to do these kind of things. Okay, simple enough. No questions on addition?
Quick question on broadcasting.
Yeah, go ahead.
Is it common practice to just use broadcasting, or is it kind of just like, I have no other way?
So yeah, usually broadcasting will be used quite often because it's shorter and it makes a lot of the algorithms a lot easier to write versus having to like create a new vector or a new tensor to add them together. It just kind of makes it a lot quicker in that way. So you'll see broadcasting quite often. And I've seen like, I remember in one text, they spent a whole chapter talking about broadcasting and all the different ways and why it doesn't work and why it works in certain ways. Basically, it comes down to the fact that like, oh, we can use efficiencies to make this work well too. So you'll see it quite often and you'll probably use it yourself. But it can be kind of confusing and intimidating at first. But anyway, this kind of leads us into what happens when they have different dimensions and we try doing broadcasting. So again, sometimes broadcasting or NumPy is really good. It's like, oh, I know what you're talking about. So here I add a 3 by 2 matrix by 1 by 2. So these are all 2D stuff, right? So you can see right here, I just have basically a 2D, or sorry, I can't talk anymore. This is just a vector right here. Okay, and I add that original matrix A. So I just get rid of this for a second. You can see this is our full matrix right here. And I'm just gonna add 100 to it. Well, this vector by itself just show you what x looks like. That's our vector right here. You technically shouldn't be allowed to add a plus x, but what is nice is that through broadcasting, you would expect, oops, well, never mind, that didn't work because I changed the values. Sorry, I originally had it as a 3x2. That's probably why. So if I add this part, 0, 1 right here, okay, you can see our vectors are 0, 1, 2, 3, 4, 5. So if we added a shape of 2 vector, you would expect like, oh, I want to just add that vector to this one, that same vector to this one, that same vector to this one. And that's what broadcasting ends up doing. So we can see a 3x2 added by a 1x2. We can now see I just added 0 to 100 to each element in there. Okay, because originally this was 1. Sorry, go ahead.
So it has its nuance, but technically it's supposed to make sense before you even attempt to broadcast.
That's right. It's making sense before you're doing it, essentially.
Okay.
If it doesn't make sense, like you saw earlier, it'll give an error. So it will throw out an error saying, hey, you can't do this, or I don't really know how to do this. But if you know, if like you're trying to say, well, I want to add this little vector to each one, it'll say, oh, okay, I think I know what you're doing. Again, technically, you should have like a vector of like an array of vectors. Okay. Oh, did someone have a question? Okay. I think Jonathan's mic went on. I couldn't quite hear him if he was. Okay. Anyway, so that's this one right here. You can see right here, we can do something similar when we just have the same dimensions. If we have the same dimensions, it just adds it up like we saw before. If we tried adding things that did not, I don't know why I wrote it like this. If we have one that's not it should be added by a 3, 2, or 2, 3. You can see I reshaped that vector into a 3 or a 2, 3. And if we do this, like we saw before, we'll get an error saying, hey, can't be broadcast together with shapes 3, 2, 2, 3. So that's why we get an error here. Okay. Any questions on broadcasting addition like that? Okay. And you'll see broadcasting not just for addition works for other mathematical parts. So if we have like multiplication here, which we'll talk about, we actually have 2 different types of multiplication that we see often. Or since like 2, there should be 3 actually. But there's the Hadamard product, and the Hadamard product really is similar to like how you would think like with adding element to element. It multiplies element per element. So if I have these different A and B here, right? I can do this multiplication. This is the Hadamard product, and what will happen is we'll multiply each element by itself. So 0 times 0, 1 times 10, 2 times 20, and so on and so on. So we'll see here, we'll get one array, and it'll still be a shape of, what's this, 3, 2. So when I do this now, you can actually see I get still a 3, 2 shape, but it just multiplied each element per element. That's what's going on here. Okay. This is not typically used very much for most things that we're doing. Most multiplication is probably going to be a dot product. We'll also talk about cross product in a second. This tends not to be used very much, but it's good to know. And note that that's where this multiplication is. I think the curriculum actually shows another way to like NP dot. I don't remember what the function is, but you can just use this star here. So that's important to know, is that even though we use the dot very, very often, this is not the dot product. This is the Hadamard product. So be careful with that when you're doing you're doing a calculation. Okay, and we can see it does, we can try doing broadcasting, for example. So we have a matrix 0 to 100. So you would expect, oh, I kind of want to do 0 to 100, 0 to the first element, 100 to the second element through all the vectors. And you can see that's exactly what happens here. Okay, so that's another broadcasting. This one, it's just when it's the same, just like we saw with A and B, with the same dimension, we just do it across. And then of course we have the one that doesn't work. And we try doing that one, which again, I don't know, I put 2 by 3, it should be, or 3 by 2, it should be 2 by 3. So anyway, you can see right here, I can't broadcast those parts together because NumPy is like, this shouldn't work. I don't really know what you're trying to do. Okay, so Hadamard product, pretty much like addition, element by element, works essentially the same except they're multiplying together. So that brings us to dot product, which is probably the most common of all our multiplications that we'll tend to do. And so note that there is a very specific way we do dot product. meaning that if you do not have this dot, it likely will fail. I'm trying to remember specifically if there's broadcasting. I believe there isn't. I could be wrong, but I'm almost guarantee there's no broadcasting, and it's because we need the specific shape. If you broadcast, it would mean that you could accidentally make a dot product when it shouldn't happen. So that's why my guess is that there's no dot broadcasting and dot product. But again, if you guys find something different, let me know, because we make a mistake. But you can see I have this M by N matrix, and I have an N by P matrix, and I can multiply them together to get an M by P. So the way I think of it is like it gets the outside one, number of rows, number of columns, and that's what the resulting matrix is. So in this case, I actually created A, and I just, for B, I did a transpose of that so we can get something that's a different shape. It'll actually work. So you can see I have my A right here, and I made my B or my C right here, which is just a transpose of A, or of B, which is just flipped over or turned off to the side. And now I can show you how to do the dot product. So there's basically like, you can see there's three main ways of doing the dot product. You can just do the NumPy function and then pass in AC. You can do the array dot C, and this, I see this very commonly. You can also do a, and that's just the @ symbol, C, which I like to use because it's quicker. I don't know, some people have preferences of why you might want to do this, but they call the same function. They should be calling the same function. So there's not like a difference in that sense. It's just more like notation, different ways you can do it. But when we do AC, what's going to happen now, it's going to essentially be multiplying these parts together and adding them together. So I'm not going to hang too much detail on this because the curriculum does show you in full of what the dot product looks like and all those parts, but I just wanted to show you how you would do this with NumPy. So you can see here is that I'll get a matrix of 3 by 3 because I had a 3 by 2, a 2 by 3. So the ones that stay are 3, 3. Okay. Any questions on this that I just showed? Okay. Just know that to get each of these elements, you're basically multiplying parts. If you guys remember back in like school, it's like row times column. So you go across each row multiplied by the column. So you go like 0 times 0, 1 times 10, add up those parts, and that'll give you 10. The next one would be 2, 3. So you get 2 times, I'm sorry, next one would be 0, 1. So it'd be 0 times 20, 1 times 30, and gives us this element right here. And you kind of just go through that whole thing, that whole process. Again, curriculum goes through a lot more, so look that over. There's plenty of stuff that you can read about the dot product. I don't need to show you guys in this short amount of time, but at least this is how you can do that calculation. And then you can see if I try broadcasting it on this wrong shape, it doesn't work because the dimensions don't add up right. So, cool. All right. Oh, that's kind of cool. I didn't know that existed. There's Stack Overflow. This is Colab. So, okay, and that brings us to our last cross product. Or sorry, our last way of multiplying things is our cross product. And cross products are usually a way, I should probably share this video. There's a good video, to be honest, it's like 20, 30 minutes long, but he does a great visualization of like intuitively understanding what matrices are and what it means to multiply and add them together. I think it's a really great thing. Maybe I'll share this out, but it's too much for me to go into detail. But cross product, again, curriculum goes through more detail of exactly what it is. Use a cross product usually to to span a new vector. So you can create a new vector out of these two other vectors. And by vectors, it could also mean matrices. A matrix in a lot of ways is representing multiple vectors. We can talk more about that when the interpretation of what a matrix is. But you can kind of think of like, oh, a matrix kind of spans a space. It's a bunch of vectors spanning a single space. And that means that a tensor could be like a three-dimensional tensor. It's a thing of matrices, so it's spanning multiple spaces. It again gets kind of fuzzy at this point, and our brains start hurting. At least mine does. But you can see we can do the cross product, np.cross. In this case, I'm just getting the first vector here, the second vector here, and then I'm doing a cross product. And I don't actually understand why that gave me a -2. Is that right? Sorry, guys, I'm thinking. Oh, put the same thing. This should give me 0. Okay. Okay. Yeah. It's because they're one-dimensional. I have to think about that for a second. But basically, the main thing with the cross product is that it should produce the same of the same shape. So maybe if I do dot shape, you can see what this is. Okay. Oh, because I'm doing on print. Interesting. Okay. Let's give this a scalar. I have to double check what I'm doing here. Am I? Sorry, I caught myself in a middle of like, wait, that's not what I expected. I wonder if I tested this out with a 5x3. Okay, that makes more sense now. Okay. So I think I tried it with a smaller shape in this case. Oh, it's probably because, okay, sorry. Okay, there we go. Sorry, guys. I realized they were probably, there was something else basically where they were, okay, so you remember how I said the two vectors, if I do a cross product, it'll make a third vector? The problem is that if those two vectors, if one vector is basically a scale of the other one, it doesn't make sense to make a third dimensional vector. So what happened is that I was getting a vector that was dependent on the other vector. So I was actually end up getting one dimension lower. Basically, you say, oh, these two vectors only span a one-dimensional space, so I'll give you a second vector that's a one-dimensional space. But if you have two independent vectors, this is more linear algebra stuff, but you have two vectors that basically cannot be written by, can't be written as itself. Like you can't do like a multiplication of this vector to get this vector. You will get a third vector, and this third vector will be perpendicular to both vectors. That's why you end up getting this part. Again, there's more detail in the curriculum, but I just wanted to show you at least how to create this part. But it should give you, if they're independent, a vector that is of the same dimensional shape, or sorry, the same shape. Okay, cool. Any questions on that one? That one, I kind of threw you guys a little curveball. I threw myself a curveball. But anyway, so easy enough right here. Okay. And then our last part, I know we started a little late, so if you guys are good, I'll keep continuing a little bit for the last 5 minutes. Okay, good. The last one we have is manipulating matrices. And so there's two important parts, identity, inverse. So one thing I kind of skipped over is that you can't, we talked about multiplying matrices, right? Or it's not matrices, but tensors in general, with dot products and cross products and stuff like that. Multiplication, you can't divide out a matrix. It doesn't really make sense in that way. And it basically comes down to the fact that it's a different kind of algebra. And if you didn't know, algebra actually has many different kinds of algebra, algebrae, I don't know, but whatever the plural is for algebra, there's many different ones. So it turns out in matrix algebra, you can't actually divide in that same sense. You can, however, do something called an inverse, which is kind of equivalent to dividing. Like, for example, when we do an inverse of, the inverse of 2 is, anyone got an idea what the inverse might be when we talk about multiplication versus the number 2? Half. Good. And basically it means that if you take those two, numbers, those two things, and you put them together, and by putting them together, it usually means multiplication, but we put them together, they should give you what we call the identity. And the identity is basically, it produces the same thing over and over again. So there's an identity matrix, and our identity for multiplication for the integers or for, the real numbers is just the number 1. Because you multiply 1 by anything, gives it whatever you multiplied it to. So identity matrix, you'll see something very similar, is that we'll actually see that it'll give us the same thing when we do dot product. So this is how we can define a identity matrix for in NumPy. And you'll notice that it's, I made this matrix right here, 5 by 5 matrix. I can do a matrix called I, and it'll be 5 elements in there. And it's called I because you're making, usually we'll talk about the identity matrix and it's labeled as the letter I. And of course, they didn't want to put the letter I there because that would be more confusing with imaginary numbers. So they have it as EYE. So you can see now, if I have the identity matrix right here, you can see this is my identity matrix, and all identity matrices pretty much look exactly the same. They're all square, meaning that they're 5 rows, 5 columns. They have 1s across the diagonal and 0s everywhere else. So for example, if I put identity matrix of 3, you can see it's 3 by 3, all that stuff. So they all look kind of very similar. But what the nice property about this is that now if I multiply with the dot product, the identity times a matrix, either direction, because remember, matrices aren't necessarily, you'll learn this in the curriculum too, is that they're not necessarily commutative. You can't simply just switch them over. But we can actually see, okay, when you multiply these together, you actually get the same thing each time. So you'll get A. So this is A, this is A, and then I do this little part where, are these guys equal to each other? And it compares it element by element, and it's true, 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 true. Note that this right here can be kind of tricky because when we do things like, we'll look in the inverse matrix, this will actually not produce, this won't always produce equals because of rounding errors, essentially. In this case, it was fine, but note that sometimes even though they should be equal, your output will not be equal because of rounding errors. So you have to be careful with that, or at least be aware. Okay. This brings us to the inverse matrix. So our inverse matrix is basically taking a matrix and using another matrix to get to the identity. And that's what our inverse is. So in here, I just actually defined 2 matrices, and you'll see, oh, those are some interesting numbers, Victor. Why did you pick those numbers? Oh, because I am a wizard, and I realized that these matrices have a special relationship between the 2. And as you might have guessed, is that they are actually inverses of each other. So when I multiply x times y with the dot product, y times x, I actually get the identity matrix. These are not trivial to find from each other. So note that most index or inverses will not be integers, even if you started off with integers. Most of them will be some fractional value, if they even exist. Not every matrix has an inverse. So something to kind of keep in mind when you do that. And also note that inverses aren't really defined if they're not square. If you have more rows or more columns, so if you have like a 4 by 5 or a 3 by 2, you can't technically find an inverse. You can maybe modify the matrix so you can find something that's like an inverse, but it technically doesn't have an inverse. And it's partly because you have to be able to do x times y and y times x in order to actually have to say that's a real inverse. It shouldn't matter if your inverse is multiplied first or second. So again, more mathy things, but just know that that is an important distinction. Okay. So anyway, I defined this part, but if you wanted to find the inverse of a matrix, so I define this matrix here, it's a 3 by 3. You can actually use NumPy's linear algorithm right here to basically find the inverse. And you can actually find that inverse in here, and you'll see that inverse is not very pretty. It's got these extra decimals and stuff like that. And there's actually an algorithm that's trying to find what the inverse is. And you can see now, if we multiply together, you'll see that it's not quite the identity matrix. You'll see these ones here, but you'll notice that this is slightly not 0. It's close to 0. That's a very, very small number, 10 to the power negative 17. But it's not exactly 0, and that's because of those rounding errors. So just be aware of that kind of stuff. It's like this is like the inverse, but because of rounding errors, it's not quite exact on there. Okay. And you can see here, I can just do it whole one step. Oh, sorry. This one shows this one doesn't have an inverse. So even though I have this matrix here, it's square, it turns out this does not have an inverse. And part of the reason why is something you can go into details about this for linear algebra, and they study this reason of why you don't have it. It ends up you can do a quick shortcut called the determinant to figure out if these don't exist. But basically, it's called a singular matrix, meaning that it doesn't have an inverse. You can't invert it, which is very different from our math. In our math, for the integers, we always have or not integers. For the real numbers, we always have an inverse. We can always do something. That's not true for matrices. Okay, so I know I kind of went a little bit longer than typical, but do you guys have any questions on inverse, identity matrix, anything that we talked about? Okay, cool. Thumbs up, feeling pretty good about it. Okay, hopefully it's not too much. Yeah, I see some sides. That's okay. Definitely go through the curriculum because the curriculum has a lot more detail and go into there. Hopefully this will give you an idea of what it is. I mostly wanted to show you the different ways to use NumPy and actually do the programming part. The curriculum does a lot more of the math part, which I think obviously is important. It doesn't note that it doesn't give you all the math too. It's not going into full proofs and stuff like that with why these things are. So just be aware of what's out there, and that if you kind of ask yourself but how do we know this, or are we sure? There's actual mathematical proofs that you can look it up. Wikipedia is actually a really great place to start off if you're interested in doing that math stuff. They'll have great resources. But anyway, all of this though, just to say, between math with tensors and our intro to linear algebra, that actually will lead us, and this is inside the curriculum for section 13, how to solve systems of equations. And basically, you'll find out is that as you try to do solving systems of equations, you'll find out that you can do it with linear algebra in the way that we just described, by basically finding the inverse and essentially finding those values. But it turns out for very large matrices, it's not very efficient. And that's actually one of the big reasons why linear regression can be really difficult to use, because linear regression basically relies on solving systems of equations. And so since it takes a lot of computing power to figure out the inverse matrix, it turns out it might be easier to do other algorithms, including something we'll talk about, gradient descent, which will be into the next section. Okay, cool guys. So I think I'll leave you guys there. I won't go over this right now. We might be able to talk about it next time if you're curious, but I'll see you guys tomorrow.